Look closely at a drop of water. It appears perfectly still, but suspended inside are tiny, lifeless particles that never sit quietly. They zigzag and drift as if they are being shoved by an invisible force. In 1827, Robert Brown watched this erratic dance through a microscope like this one. Because he was observing pollen grains, his first hypothesis was logical. He assumed the movement was a biological function of living things. But the biological explanation failed. Brown repeated his experiment with inorganic materials, rock scrapings, glass dust, and soot. No matter what he used, the restless motion remained, proving that whatever was happening had nothing to do with life. This inescapable movement, later called Brownian motion, revealed a physical phenomenon that science couldn't explain. Something was acting on matter that existing laws of physics simply did not account for. By the late 19th century, the mystery took on a new weight. Chemists were already using atoms to calculate how elements combined, treating matter as if it were made of discrete units. Yet influential scientists like Ernst Mach and Wilhelm Ostwald remained unconvinced. They argued that atoms were merely mathematical bookkeeping devices, useful for balancing equations, but not necessarily real physical objects existing in nature. Their skepticism was based on a simple problem. No instrument could see an atom, and no one had measured one. Without direct observation, the atomic picture was just one of many mathematical models that happened to work. To settle the argument, science needed more than utility. It required a physical, measurable bridge that connected the visible world to the theoretical atomic realm. The answer lay in the way we think about heat. While a glass of water looks calm on the macroscopic level, the molecular theory suggests a far more violent reality. In this view, temperature is the manifestation of invisible molecules constantly moving, colliding, and exchanging energy. On a microscopic scale, collisions are not perfectly uniform. At any given instant, a suspended particle might be struck by a few more molecules on one side than the other. These statistical imbalances result in a tiny physical shove. These continuous, random impacts from every direction perfectly recreate the endless, erratic jittering that Robert Brown had observed decades earlier. The visible particle became a messenger. It was carrying physical information from an invisible molecular world. In 1905, Albert Einstein moved the story from observation to rigorous theory. Einstein understood that qualitative descriptions are incomplete. For a theory to be taken seriously, it must produce specific quantitative predictions that can be verified in a lab. He developed a formula to calculate how far a suspended particle should wander over time based on statistical rules. He then linked this wandering distance directly to Avogadro's number, the enormous constant that defines exactly how many molecules exist in a substance. This created the ultimate scientific test. If atoms were real, the microscopic noise would obey Einstein's precise statistical laws. If the measurements failed to match, the atomic theory would be in serious trouble. The task of testing that theory fell to Jean Perrin. He worked in a laboratory environment like this one, meticulously tracking the behavior of particles to see if they matched Einstein's math. Perrin used multiple methods. He tracked the wandering paths of particles and measured how they distributed themselves at different heights within a liquid. The results were undeniable. Perrin's independent experimental paths all converged on the exact same value for Avogadro's number. Even more remarkable, this value agreed with estimates coming from entirely different branches of physics and chemistry. While a single measurement can be a fluke, multiple independent methods reaching the same answer make it nearly impossible to deny the physical reality of the subject. The debate was settled. Atoms were no longer hypothetical tools for math. They were recognized as the physical building blocks of our world. This proof reinforced a strategy central to science. We often learn the most about the invisible by measuring its influence on things we can see. This same logic allows astronomers today to detect exoplanets by watching stars wobble, or to infer the presence of dark matter from gravitational effects. Today, we take this atomic reality for granted, even in the most mundane objects. We know that a pencil mark is made of graphite, composed of layers of carbon atoms. We accept this fact not because we can see the atoms, but because their existence was proven through the precision of earlier experiments. By following the jittering particles in a drop of water, scientists turned random noise into evidence, revealing the invisible architecture building everything we touch.